Beth.
And I'm Beth.
Welcome to Physics with Beth and Beth. Hello, welcome to Physics with Beth and Beth. I'm Beth. We're on this review videos that we're doing for this upcoming exam. Remember, hang in there. You can do this. We're just going to jump right in. We've got a free response question here. There are 4 types that you'll see this year. I would put this one under the quantitative, qualitative category. All right, we have a tire that is rolling without slipping. So let me explain the problem. We have a tire up here. It starts at rest on this ramp. It's going to roll down the ramp without slipping. It starts at a height h, and the ramp has an angle of theta. All right, it says that it's rolling without slipping. To remind ourselves what that means, rolling without slipping is this thing is rolling down the ramp. It's not, and as it turns, every little surface is touching the ramp. And when it does that, it has static friction. All right, and we've talked about that in an earlier video. I did the tire and showed how the velocity at the bottom, the part that's touching, every time it rolls, every little piece that touches has static friction. The velocity is 0, and that helps produce the torque to get this wheel to move. All right, now what would, if it didn't have static friction, if it was slipping? If it was slipping, then only one surface touches and it just slides down, and then you would have kinetic friction. So this is rolling and it is not sliding, no kinetic friction, only static friction. And then it says, hey, static friction is 40% that of the force directed opposite that static friction. So that's going to be important to know. They're also going to tell you, hey, the hoop, this tire is made up of a hoop and 3 rods. And those rods each have a mass of m, and the hoop has a mass of m. So the hoop is mass m, and each of the rods is a mass m. So this thing really, we have m, 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 and an m for the hoop, is really the mass total of this tire is really 4m. That's going to be important to note as we work through this problem. They also give you the moment of inertia, the rotational inertia of a hoop is mr squared, and for a rod that's rotated on an end, it's 1/3 ml squared. And you're like, why rotated on an end? Because as this tire is rotating down the ramp, that rod is not being rotated in the middle. It's being rotated on its end. And so they gave you that 1/3 ml squared. Let's just get going. First thing it says is find a free body diagram. Now, this is going to be interesting to note, and I'm going to draw a ramp. They would have given you this already on your sheet of paper for you to put on, but I'm going to draw this kind of big here. All right, so they're going to say, hey, do a free body diagram, but this one's a little different. I've told you, I think in the first video on review, sometimes they'll say, hey, make sure the forces, the length of your forces represent the magnitudes. That means you've got to draw them. If you have a force that's bigger than the other one, that arrow needs to be longer. In this one, another thing they do sometimes is place the forces where they actually occur. All right, well, first of all, this is on a ramp, so we know that the ramp is pushing at a perpendicular, our force normal, so there's 1, and that's from the ramp, the actual surface. So I'm not going to put it in the center of gravity, I'm going to put it from the surface. And then I know static friction is back up the ramp. If this tire is rolling down the ramp, static friction is, and that's a capital F with a little f and a subscript s for static friction. You could also just do little f with an s, but that is up the ramp. And then we have force due to gravity. Force due to gravity is from the center of the object, center of mass, and it's straight down, and that's going to be our force due to gravity. Those are our 3 forces. Normal force from pushing, from the surface pushing, force due to gravity straight down. That looks a little angled, but it should be straight down, of course. Earth is straight down. And then we have that static friction up the ramp. Okay, perfect. Now, they're going to say, hey, find an expression for acceleration. Okay, this is where my students probably got tired of hearing me say this, but let the problem guide you. All right, we want an expression for acceleration. That's linear, that's not rotational. So they're not talking about this thing rotating. They're talking about what is the linear acceleration as this moves down the ramp. I just did a free body diagram. I think I'm going with Newton's second law. because I already have my acceleration in that expression, and I've already been drawing some things for my free body diagram to know my forces. So then I'm going to just start right in. I'm going to know that this acceleration down the ramp is parallel to the ramp. So I'm looking for my parallel forces. So I have parallel to the ramp. Here's my ramp. Parallel to the ramp is static friction. I'm going to call that negative. Why? Because I always like to direct movement as positive. That way my acceleration is positive and I don't have to worry about putting in a negative here. All right, it's moving down the ramp, so I'm going to call that positive for acceleration. That means static friction is opposite, so it's negative. Now, the only other force that I have that is parallel, and I'm going to never put your components on your free body diagram, so I'm going to draw this over here so you can see it. I had force due to gravity that was down. All right, but if this is my ramp, then I have a piece here that is perpendicular to the ramp. That's force due to gravity perpendicular. And then I have another force that's parallel to the ramp. This is my ramp. That's parallel to my ramp, and that's force due to gravity parallel. And if that's theta, this is theta, that's opposite it. So I said in that last review video some equations to memorize. This is a good one, so you don't have to keep drawing it out. I would memorize that force due to gravity parallel is mg sine theta, because it's force due to gravity times opposite, that's opposite sine theta. So I have a plus, and that's down the ramp, which I've defined as positive, mg sine theta. Now, opposite that, perpendicular force due to gravity is mg cosine theta, because it's adjacent to that angle. So it's mg cosine theta. All right, but it's perpendicular. We're only worried about parallel forces. And that's going to equal mass times your acceleration that we're looking for. All right, so now we just have an issue here about what is the static friction force. Well, they made this comment. They said, hey, static friction is 40% that of the force directed opposite static friction. Well, this is the opposite static friction, the force. And they said, well, your static friction is 40% of that. So I'm just going to put in negative, because the negative is still there, 0.4, because it's 40%, mg sine theta equals, plus mg sine theta equals mass times acceleration. Now, before I go any further, we've got to talk about this issue right here, that the mass of the tire is actually 4m. All these masses were mass of the tire, right? Mass of the tire. All of them. Well, we know mass of the tire is really 4m because the hoop was one mass and the 3 rods were each a mass. So I'm now going to sub that in. I have negative 0.4 times 4m g sine theta plus 4m g sine theta equals 4m times your acceleration. All I did was for my total mass put in 4m. Well, Q Party in the USA, have a little dance here while we mark off, because everybody brought 4m to the party. And now I have a negative 0.4 g sine theta plus g sine theta equals acceleration. Well, that's like saying 1. These are like terms. 1 minus 0.4 is 0.6. And I get 0.6 g sine theta is your expression for acceleration. Now, we didn't get any numbers. It's quantitative, qualitative, not a mathematical, and you could leave it like that in that expression. Now, some things to note. First of all, watch that free body diagram on what they asked for. 2, make sure that you just don't jump to something, all right? That you will get sometimes points for if you put in this, if you had just jumped and, I don't know, just got down here to 0.6 and kind of did this all in your head and said, oh, I get it, that this force, this parallel force due to gravity is down and the static friction force is 0.4. Well, that means that it's just 0.6. and it's got to be 0.6 g sine theta because the masses cancel out, and you try to do that all in your head. That's great if you can do that, but you would have gotten to the right answer and you wouldn't have gotten all the points. All right, because they will give you a point for, for static friction, they're subbing in 0.4 mg, really 4 mg sine theta. You would have gotten a point for this most likely. And if you get to the right answer and do it in your head and you didn't show the substitution for your static friction, then you would have not gotten that point. And you may not have to write it as much as I did and write this step and then this step. You could have probably went from here to here. But anyway, just make sure that you're not trying to do this all in your head and just write out an answer. You might lose some points. Okay, now C, the next thing we're going to ask for over here, that was free body diagram, expression for A. Now they're going to say, hey, find the total rotational inertia of this tire. Okay, well, we know that the sum of our rotational inertia is going to be the rods. So we have 3 rods, and we have a hoop. Oh, whoopsies. And we have a hoop. All right. Well, the rod is 1/3 m, the mass, times L squared. Well, isn't the length of this rod, if I were to blow this up, here, I'm kind of running out of room to blow it up. If I blow it up here, this rod's length is the radius, right? There's 3 of them. So the rod length is the radius. So I'm going to put in r squared here. And I have 3 of them, 1, 2, 3. So I'm just going to do a times 3. And that's going to be my total plus, for those rods. Then I have the hoop, which is mr squared. All right, now we have to look at this. So, and we have the mass. Now you're like, why didn't you do 4m here? Because this isn't the total mass of the whole tire. This is the mass of the rods, and there's 3 of them, and this is the mass of the hoop, and there's 1 mass. So now the 3 divided by 1/3 is just 1, and I have that my rotational inertia is mr squared plus mr squared, which means 2mr squared, and that is my total rotational inertia. Okay, so that's C. Now D, it says find an expression for the velocity at the bottom of the ramp, and you can use the constants mh and constants. I mean, you can use the variables mh and constants. Same thing that they told us in B. Notice we didn't need mass, and that's okay, don't freak out. They give you something extra, they're just trying to make sure that you're just not going to use these 3 and try to come up with something randomly. They're going to want to make sure that they might give you an extra one, they might not. Okay, now I'm going to again let the problem guide me. I'm looking at this ramp. I start at rest from a height h. They want final velocity down here at the bottom. And I'm thinking, oh, I see a change in height. I know I'm at rest, so that's all potential energy due to gravity. I know at the bottom of the ramp I'm at 0 meters, so that all got converted to kinetic energy. I'm going to use conservation of mechanical energy. And doesn't that make sense that when I get to that kinetic energy, I'm going to have velocity in the equation? And that's what I'm looking for. So I'm going to do that, and I'm going to go ahead and I'll come over here to make this, that mechanical energy before equals mechanical energy final. I know at the beginning I have potential energy, and I know at the bottom I have kinetic energy linear because it's moving in a line, but it's also rolling without slipping. So I have my kinetic energy rotational, or what my students like to call caret. Sometimes they say K-rod if they don't put the E in, but caret. So you have 2 types of kinetic energy now. You have the one that's linear, translational, like the wheels on the bus go round and around, but the bus goes down the road, so linear. And then this kinetic energy that rotates. All right, I'm going to do, remember, potential energy is mgh, but remember, my object has a mass of 4m. So that's going to be 4mg, little g, times the height. My translational is 1/2 the total mass of this, which is 4m, times v squared, plus my rotational is 1/2 my moment of inertia for the total system times that angular velocity squared. Okay, this is looking good, except I do have my velocity, which is what they want, an expression for velocity. except that I have velocity here that's translational, meters per second, and I have an angular velocity that it's radians per second. All right, we can't add those up. They're not like terms. So we're going to need to go and come up with an expression for angular velocity related to velocity. And oh, we're going to remember, hey, I know that. That's r times velocity, linear or translational velocity is radius times your angular velocity. I'm going to divide both sides by r, and I get that velocity divided by r is equal to angular velocity. Well, this one's squared, so I'm just going to square everything, and then it all stays the same. And now I have an expression to put in for that angular velocity, and I'm going to do that. So I have 4mg, I'm going to write this out, 4 times mass times little g times the height equals 1/2 times 4 times the mass times velocity squared plus 1/2. Oh, and look, I need the total for this hoop. Oh, let the problem guide you. I just found that in C. So I'm going to use 2 times the mass times r squared. And my angular velocity, I just found an expression for that. It's v squared over r squared. That's a v. All right, so I just subbed in this expression for my angular velocity squared. For my total rotational inertia, I subbed in what I found in C. Okay, now I'm going to try to simplify this somehow. 4 divided by 2 is just 2 mass times velocity squared. 2 divided by 1/2 is just 1. My radius is I have an r squared on the top and r squared on the bottom. So that's just going to be mv squared because the 2's become 1. This becomes 2. 1 mv squared. All right. Oh, look. Everybody brought mass to the party. Cue party in USA. And mark that out. Do a little dance party in the USA. And we have 2v squared plus v squared. That's going to be 3v squared equals 4 times little g times height. I'm going to divide by 3 and then take the square root. So that's going to be 4g little g times height divided by 3, and if I take the square root, that'll be v. All right, that is the expression for velocity, and that is done. Now, there's one final question they're going to ask here. What if you replace that tire for a block of ice, and you're assuming no friction, which has the greatest velocity at the bottom, and justify? Okay, here is a very good tip on when they ask you if you change this, what happens? If you add this, what happens? If you cut the string on an Atwood machine, what happens? All right, first answer the question. And I know that sounds silly, but I'm telling you, after grading years of practice tests in my own classroom, I can tell you, you just want to start jumping in and explaining it. But you never really answer the question, and you might lose a point for that. So make sure that you answer the question, or if it's got a little box there to check which one, make sure you check it. You don't just jump into the explanation. All right, so if I replace this thing with ice and there's no friction, which one's going to have the greatest velocity at the bottom? Well, it's going to be the ice. So I'm going to say the ice will have the greatest velocity. Oh, whoops. We'll have, and I'll explain that if you don't see it, we'll have the greatest velocity. I'll call it final velocity. Now they may just have a box for you to check, and then that's great. That makes it easier. Just don't forget to check one of the boxes. It might say ice or the tire. Ice will have the greatest final velocity. Now then, because you do get points for justifying. So because, and here's why. Because the ice is not rotating. So none of the mechanical energy of the system gets transferred into making the object rotate, because that's what happens here. You had a total mechanical energy of a system, but part of it had to get used right here. Part of it had to get used to make the tire rotate. When you have ice, you don't have this. You just have this piece. All right. So in other words, because the part, you could say part of the mechanical energy was transferred to make the tire rotate. And you could have explained it better. You can also explain it with, let's see, ice will have the greatest final velocity because part of the mechanical energy was transferred to make the tire rotate. And then you could have followed up, I'm just making this video so long, and the block of ice, all of the mechanical energy was in the translational kinetic energy because none of it was needed to make the ice rotate, to use as kinetic energy. You could have said something like this, so this is probably not quite complete. You could have also used the equation. You could have come back up here and you can always use an equation or words, but unless it specifically says words, then you got to use words. But if it doesn't specify, you could use an equation. This just went to kinetic energy. So then it's 4mgh. It would, and the block, they would have told you that for a block of ice that was the same mass as the tire. Same mass as the tire, so that would have been 4m equals 1/2 4m velocity squared. Well, that becomes 4mgh equals 2mv squared. Masses go, divide by 2, and you get 2gh. The square root equals the velocity. All right, well, the square root of 2 times little g times height is greater than the square root of 4/3 times little g times height. So you could have proved that in an equation as long as it didn't require words. If it requires words, you got to answer in words. Okay, all right, and again, this was probably not complete, but I don't want to waste your time writing all of that out. The bottom line is with ice, there is no mechanical energy that has to be transferred into getting it to rotate. All right, and there was no friction, so you're not losing any friction, kinetic friction. You're not losing any energy due to kinetic friction from the ice sliding down the ramp because they said no friction. All right, so that's the other component of that. If there's no friction, there's no kinetic. If there's no friction, no kinetic friction, so no energy being lost from the system. Okay, I hope that helps. We went through a free bite diagram. These review videos are going to be long. I'm sorry, we can't shorten them. We have tried to figure it out. We just can't. So I hope you found this helpful. If you liked it, please give us a like, subscribe, tell your friends if they're struggling or stressed about this AP exam and you find our videos helpful. We would love that. And thank you for watching and happy physicsing.